Problem 3. A tank initially contains 20 kilograms of water at 25 degrees C. Suddenly we have two inlet valves and a single outlet valve that are opened. You have two water streams, 4 kilograms per second, 40 degrees, 6 kilograms per second, 80 degrees. And we have an outlet T3. I'm sorry, I call it T3, but that is actually the temperature in the tank. That's the usual assumption for a stirred tank. So I normally would just call that T. And part A says calculate the effluent mass flow rate that would be expected after the system reaches steady state. So at steady state, the inputs have to balance with the outputs. We're talking about masses which are conserved. So you can't generate or consume. So M1 plus M2 would equal M3, which is just 4 plus 6 kilograms per second, which would be 10. Okay, remember I advise you not to calculate numbers, but that's pretty easy to calculate. Part B says, consider the general energy balance. This would have been given during lecture for a flow system, and note that it does not assume steady state. Okay, indicate which terms in the energy balance equation would be affected by the following phenomena. Okay, number 1 is work done by fluid pushing against the outlet pipe as it leaves the tank. Well, this is going to affect the enthalpy, which is this term. That is, remember, when we originally did the balances, we were balancing energy, but then there was a PV work term that was associated with the work required for fluid to enter and leave the tank. Okay, number 2 is steam flowing over the outside of the tank to warm the tank's contents. Well, that would be Q. That'd be this term. That would be heat entering the tank. The steam is outside the system technically, but it can exchange heat unless it's insulated. Let's see. An impeller stirring the contents of the tank. Well, that would be work. And an expansion or contraction of the tank. That would also be work. Okay. Now we have to calculate the temperature of the water in the tank at steady state, neglecting heat exchange between the tank and its surroundings or changes in the gravitational potential or kinetic energy. So I'm going to change colors here, and this problem is going to associate with the pink color. And let's see, if we're neglecting the gravitational potential, then this term would be 0. If we are neglecting heat, then this term would be 0. The kinetic energy refers to the velocity, so that term would be 0. Assume the tank's contents are well stirred and that 100 kilowatts of power is required to perform the stirring. So this is actually 100 kilowatts of work per unit time or power. This is the only work done on the system other than flow work. Treat the heat capacity as constant at 4.18. So now we have to, let's see, is this a steady state problem? Yes, it is steady state right here. Okay, so the time derivative would be 0. This would also be 0 at steady state. And we need to balance the enthalpies going in and out. So the enthalpy in will be m dot 1 Cp T1 plus m dot 2, dot 2 Cp T2 minus m dot 3 Cp T plus 100 kilowatts of work. Now notice that I didn't actually imply a reference temperature here. I actually should have said T minus T ref for each of these terms because enthalpy could be considered relative to some reference state. But I believe that I can arbitrarily say that this is in, I could choose my reference temperature and it actually arbitrarily, as long as there are no phase transitions, and it should not affect things. So what I'm actually implying here is that we're choosing a reference temperature to be 0 Kelvin, but actually I think if you chose any other reference temperature, you'd get the same answer as long as there's no phase transitions. And so I think we actually have all the numbers we need here. So M1, yeah, so this is 4 kilograms per second. This is 4.18 kilojoules per kilogram Kelvin. And this would be 40 plus 273 M2, put it up here, this would be 6 kilograms per second. Cp is the same as 4.18, and T2, I believe, is 80. 80 plus 273. M3 at steady state is equal to 10, 4.18, and this is what we actually don't know. This is the only unknown. So then, and by the way, this would equal 0 at steady state, so that in the balance equation, let's see, the inputs, these are the inputs of energy, that's the output, it would balance to 0. Okay. So then we just need to solve for T. Again, I'll skip that part and come back to it. The last part is derive an expression for temperature of water from the tank as a function of time. Okay, now we have to consider the full differential equation. So that time derivative would be dmu dt would equal, well, the same thing we wrote before. So it would be m1cp T1 plus m2cp T2 minus m3cp T plus 100 kilowatts. And, oh, this looks funny. This would be dm dt times u plus m du dt. And it refers specifically to the mass inside the tank. And we don't strictly know what that is as a function of time, because the problem does not specifically tell us what M3 is as a function of time. I mean, if we assume that it starts at the steady state value, you have M1, M2, and M3 immediately balancing each other, and then the amount of material would remain at 20 kilograms, and we could solve this. But the question doesn't actually tell us that. So I actually think this is a sufficient answer by itself. Okay, now what did we not calculate? So part A we calculated, part B was just conceptual, so this would require a calculation. So this solving for T would give us 1 over 10 times 4.18 times everything else, 100 plus 4 times 4.18 times 313 plus 6 times 4.18 times 353. And this turns out to be 339 Kelvin. Okay, I think we're done.